In this video, we're going to explore the oxymercuration protonolysis of alkynes. This looks a little different than the Chapter 6 mercury reaction, but in effect it's not entirely different. The end result, as you can see though, is we added water, 2 new H's on the terminal position of the alkyne, where there was only one H before. That H is still there. And the new oxygen on the more substituted carbon. That'd be a Markovnikov addition of oxygen, wouldn't it? Mechanism starts with mercury sulfate in its ionized form, depicted here. Mercury 2+ ion and sulfate ion, same as this. The pi electrons are very attracted to the mercury, as they were in Chapter 6, generating this cyclic mercuronium ion, which will undergo reaction with water. Which carbon will be attacked? Will be the more substituted carbon. Why are these partial bonds and not full bonds? Because only this one arrow was used to make all 3 of those. They are all partial bonds. 2 electrons total. The pi electrons here are now part of a triangle, and water is going to do its thing by doing a backside attack on the more substituted carbon as depicted here. Coming in from behind, attacking the more substituted carbon, generating this next intermediate here. O on the more substituted carbon, Markovnikov result. More electronegative O, more substituted carbon. Stereochemistry is the O is on the left side of the alkene and the mercury is on the right. That's an anti-stereoselectivity, as expected whenever we pop open a triangle. And we are going to find the best base now to neutralize our oxonium and make it into an OH. And the best base around is the sulfate ion. It's going to use a lone pair. Grab the H off of the oxonium, a strong acid. And the sigma breaks and becomes a lone pair on the O, giving this result here. We now have a hydroxyl on our alkene and a mercury here. Clearly the mercury has to go away. The title gives a hint as to how we get rid of the mercury. Unlike Chapter 6, where we added a separate chemical in a second step called sodium borohydride to get rid of the mercury, here we're going to use a strong acid to cut the mercury off. Strong acids have protons. The word for cutting in science is lyse. Well, a word for cutting is lyse. We're using a proton to lyse this mercury off. It's called protonolysis. And the sigma breaks. The carbon keeps those electrons and makes a bond to H. Hydrogen sulfate is liberated here, and we get this result. Quite a bit happened here. We replaced the mercury with this hydrogen right here. I'll color it blue so you know where it came from. Mercury didn't keep any of the electrons, so it was sharing those 2. It owns none of them. It's back to mercury 2+. I'd like to remind you we started with mercury 2+. What do you call a species where you use it early in a reaction and you regenerate it later? You call it a catalyst. And what noise do catalysts always make when they come home? They say meow. This is a new functional group right here. It's got an alkene in it, so it starts with En, like alkene. And it's got an alcohol in it. It ends with OL. You pronounce it enol. Pronounced enol. And enols are not as stable as their carbonyl partners. This molecule is going to undergo a reaction where this H disappears. Some base has to take it. This sigma is going to become the pi that we call the carbonyl here. And the old pi is going to protonate using a second molecule of sulfuric acid. So I'm going to draw another sulfuric acid up here because we need it. Yes, we already used sulfuric acid one time here. And to react 1 mole of this carbon-mercury compound, you need 1 mole of sulfuric acid. So there it is a reagent. It gets used. We need a little excess, say 1/10 of a mole, to act as a catalyst for this final reaction, which has a very fancy name. We will give it a name in a second. But during this fancy reaction, which you're going to see very frequently with increasing frequency in this course and the next one, you need an acid-base conjugate pair. Hydrogen sulfate is the conjugate base of sulfuric acid. It is acting like most bases do. It's picking up a proton. The sigma is becoming a pi. There's your carbonyl. The old pi is going to pick up a proton for the carbon 1 away from the carbonyl. And this is the result. And please note that you used sulfuric acid here and you regenerated it here. In this role, this combination, sulfuric acid is acting like a catalyst, not the same as down here where it acted like a reagent. The reaction is called tautomerization. I'll write that name down here. So you see, we have this tautomerization at the end, and that creates our ketone here. Ketone. In the next video, you'll see hydroboration oxidation, where we can make the aldehyde from the same alkyne. So we have a nice way to make ketones from terminal alkynes. And what would happen if we had an internal alkyne? Good question. Well, there'd be no preference after you make the triangular intermediate of attacking this carbon or this carbon if they both have a carbon on them. So as you might have guessed, you're going to get a mixture of 2 ketones. Here they are. In this ketone, the 2 new H's ended up on this carbon here. And in this ketone, the 2 new carbons ended up, 2 new hydrogens ended up here. I'll show the new hydrogens. So also a hydration reaction. Not as useful when you're getting 2 products as opposed to our original where we made only 1 ketone. That's very useful, very high yield. We're going to do a little twist on things down here where I get rid of water and replace it with an alcohol. It actually simplifies things because if you use an alcohol instead of water, you don't have an H here at the end, you have some kind of carbon group, which means you can't do the tautomerization step. So let's do a quick copy paste and I'll be right back. Oh, don't freak out on me now. Let me explain what I did before you try to take it all in all at once. I took everything, I copy pasted it. I got rid of the ketone because you don't make a ketone, so there's nothing in the middle here. This intermediate that we made here that had an OH, because I switched water to ethanol, H is not attached to OH like water, H is attached to O-ethyl. The ethyl follows through all the way, taking the place of H up here. If you don't have an H down here, you can't do the tautomerization step, so I erased all the tautomerization materials. And this intermediate over here called an enol is now called an enol ether, and it's not an intermediate. It is the final result of oxymercuration protonolysis of alkynes using an alcohol instead of using water. You will not find this in the textbook, so take note of it now. Be ready to use it on exams. And I hope you have found this video on the oxymercuration and protonolysis of alkynes to be useful, and I look forward to our next video together.